My name is Tianzi Peng, and I'm a postdoc in the Department of the Atmospheric and Oceanic Sciences at McGill University in Canada. This presentation was based on a study that was done when I was at the University of Notre Dame working with Dr. David Richter. So today we are going to talk about the influences and modeling strategies of sea spray when the size classes are more than one, or you can say poly-dispersed. So this is a interesting question because traditionally we used to think droplets are independent, but we know that it may not be independent, and when and how we deal with this kind of assumption was not sufficiently discussed. So we are thinking to use this kind of study to have some insights into this matter. So to begin with, I would like to introduce the paper which this presentation will be based on. So we focus on the indirect interactions, meaning that the spray droplets will interact with the environment, and then the other droplets will receive this kind of influence via the ambient environment, and vice versa. Here we don't consider any droplet-droplet direct interactions. What we found that there could be a potential overestimate of the sea spray's contributions to the heat budget if we assume sea spray are independent. We also find that this issue for the double counting doesn't apply to every size classes. This is only an issue when the spray size is small. And speaking of how to determine small and large droplets, here we use a concept of timescale, the ratio between the residence time and the thermal responding time. So when we are talking about the ASI interface system, basically, there are two routes and two media. And routes we can understand as like the sensible or latent heat fluxes. And the media, it can come from the ocean surface directly. And also, what we are interested really is the spray-mediated heat fluxes. So then, two routes to media, we have four components. There are several questions. For example, does sensible and latent add together? If we add spray into the system, whether the interfacial heat fluxes will be influenced from the spray. So these two questions we have already answered in our JPO paper in 2019. And today, we based on that result, and we're going to answer the question that how do this relationship we found from a single size study apply to multiple size classes? So to begin with, if you are familiar with the way in the bulk model how the spray-mediated fluxes are parameterized, you will know that it's based on the assumption that there will be a nominal fluxes, meaning the net exchange of the heat, either sensible heat which is proportional to the temperature change, or the latent heat which is proportional to the mass change. And then you have the strength of the production rate, which people call this as SSGF, sea spray generation function. You have the different size classes, so you make the summation, and in a continuous space, you make the integral. So the question is, if we use this formula, we have already assumed that no interactions between size classes. This might be unconditionally practical if we think the spray is sparse, but if wind velocity is very high, we know the mass fraction of the sea spray above the ocean surface is extremely high. So in that case, can we still add them together to make the predictions of the total heat fluxes? And if you look at different literatures, we can find during the past decades, this is a very common way to do so. So we will just directly pull out the bulk estimation for our model with the coefficient beta equal to 1 and gamma as a negative number, which means that spray will have a negative feedback effect with the interfacial heat fluxes. So with that, those numbers were successfully applied to multiple sizes if we only consider one size. So we'll make this kind of interaction between interfacial and spray as one package. Our question is whether we need another term to correct the polydispersity when there are more than one size class. To investigate this question, we are running numerical models. Here, the model we are using is the high-resolution Eulerian-Lagrangian DNS models. The carrier flow is an open channel with flat surface, neutral stabilities, and we can vary the boundary conditions for the temperature and relative humidities, the turbulence was driven by the pressure difference on the two sides of the wall. For the droplets, we directly model each droplet through the Lagrangian droplets, and those Lagrangian droplets are point particles which has mass, but we neglect the volume effects. We assume no collisions. Thermal coupling is two-way, and momentum coupling is only one-way. So these models are fairly consistent with our previous studies with single sides. And then the difference is that we add multiple sizes. So we will start with the two sides, which is the simplest poly-dispersed sides, and then we consider more realistic size distributions. First, let's look at the Bi-dispersed cases where we only have two sizes. So I picked up three sizes, basically 25, 50, and 200 microns. These three sizes in our model, which has three different characteristics. The 25 size has very long residence time, but they respond to the ambient environment very fast. And 50 is about the trade-off between residence time and the thermal responding time. And 200 microns, those residence time are very short, but they have very slow response to the ambient environment. So there will be three groups, and we mix each of two out of three. And what we are going to do here is we're going to compare two quantities. On the left side, it is the real value from our DNS model. On the right-hand side, basically, it is a bulk prediction with the correct statistics of the temperature and mass change of each droplet sampled in this simulation. So in this figure, you can see the DNS value is on the horizontal axis, and the bulk estimated value, which is the right-hand side, is printed in the vertical axis. Three different shapes, meaning different groups. So first we will see a gray solid line, which means y equal to x. So that means bulk estimation is equal to DNS. Then two dashed line next to this solid line, meaning plus and negative 2.5% of the air. Now we can see if any mix of the two sizes contains a small droplets as 25 microns, then larger mass fractions gives a larger error of the estimation from the bulk models, which is a problem. And as I mentioned earlier, when I was selecting the sizes of these three, they have very different attributions in terms of the residence time. As you can see here, what I plotted is a trajectory in z directions of two sizes. The magenta one represents 25 microns, and the 200 one, basically you can see those are ballistic motions of the heavier one. And if we plot the droplet timescale ratio, and you can see the green line here, the solid line, represents what we call non-dimensional residence time. And for 25 microns, it's about 1, and for 200 microns, it's way below 1. So that means we have this kind of separations. For small droplets, for example, 25 microns, when they enter the water, they will make an instant adjustment based on the ambient air. However, the large droplets, they barely change. So the reason why I said this, because if we compare how much temperature is changed or how much rate is changed from the single size cases or the mixed cases from two sides, we can find that some sizes are more sensitive to other sizes. In these two panels, you can see with different size they mixed, or just the solid line, which means the single sides. 50 microns is the most sensible one among the three. And if you take a closer look, for example, if we take a look at the first panel, when being mixed with 25 microns, then the average temperature change of a droplet is lower than a single case of 50 microns. If they mixed with the larger droplets, for example 50 and 200, and then here the average temperature change of 50 microns will be higher than if only we are running the simulation with 2.5% of 50 micron droplets. That means it appears that contribution of the small droplets to the system are reflected to the larger one. So we might just overcount the small droplets heat contributions. If we go back to the previous figures about the comparison between DNS and bulk model, if now we just consider the size 2, which is the larger one, For example, if we only add nominal fluxes from the larger size, we can find that these errors are substantially improved. Now we're doing a similar thing again, but with more realistic size distributions. So here we consider more sophisticated size distributions. There are two types we're considering right now. First is the cubic decay, which means by larger size, the number of the droplets is decayed cubically, which means in each size class we have assigned equal mass in each size class. And the second one is an exponential decay. This one we consider as a comparison just purely because it was widely used and it is a simplified Andreas 1998 SSGF. We also had other comparisons. For example, we consider different resolutions of the realizations of the SSGF. Also, one group here is U-MR, the left side. We don't consider the small droplets at all as a comparison. Now we are running simulations with all these size distributions. We are going to do the similar thing to filter out small droplets. Here what we are going to do is we're going to do this based on the time scale. So if the residence time is greater than the thermal response time, we just drop it to 0. So we add a weighting at the heaviside functions before the spray nominal fluxes. And from here you can see basically between 70 or 80 microns we have to drop off, and we keep everything above that size remaining in this system. So there are three things to pay attention. First, if there are small droplets, by neglecting the small droplets contribution, we can get an obvious improvement. However, there are some exceptions. First, here in our study, we consider the lower bottom surface as saturated, 100% relative humidity. If the surface is drier, which means we don't have to worry too much about the recondensation of the small droplets once entering the surface, then it appears that it is not very necessary to consider this kind of filter because there isn't fast-paced sensible latent transfer induced by small droplets. There could be a second exception as well when there is no small droplets at all. For example, for the case I just marked here, if we just neglect the small droplets in the system, then we're pretty sure that assuming each droplet is independent is a good enough solution for this case. So I think that's all for this presentation, and I invite you to take a look at our latest paper. We not only elaborate the topics in this presentation, we also talk about the representative spray size and the way to further simplify the SSGF. We also plotted how good the bulk prediction it is in terms of each single size given a polydispersed size distribution. Thank you for your attention.